All right, so now that we have a little bit of an introduction to to elimination and to alkenes in general, let's kind of talk about some unique situations that happen when it comes to elimination reactions. So we did not see this in SN2 reactions because the nucleophile would always replace the leaving group on the same exact carbon. But an interesting thing happens when we now go to E2. And let's look at this particular example here because there are multiple beta hydrogens. I have a beta hydrogen here and a beta hydrogen here and one here. Now, these two are exactly the same. I'm going to treat them the exact same way. But I'm going to call this one beta 1 and this one beta 2. And what's interesting about this is that if the base decides to go after beta 1, then we get this alkene. If the base decides to go after beta 2, we get this alkene. And in fact, if we were to set this reaction up in lab, we would find that about 71% of the product would be this alkene. That would be our major product. And about 29% would be this product. Now, when a reaction preferentially reacts to form a particular constitutional isomer, or in this case, the reaction prefers to go after a specific region, in this case, beta 2 over beta 1, that is called regiochemistry. Okay, that prefix regio basically means that a reaction prefers to react with a certain region of the substrate over another. Now, why do you think there is this product distribution? Why is there more of this alkene versus this one? And I want you to relate it to the discussion we just had on alkene stability. This alkene is more substituted and therefore more stable, which is why it's the more prevalent product. We call this more stable product the Zystev product. This alkene over here is less substituted and therefore less stable. And we call this the Hoffman product. So I want to emphasize that both products get formed. But the more stable product is formed in a greater amount. We refer to this as Zystev's rule, is that the Zystev product is the more favored product. Now, there is a way to influence this reaction to get more of the Hoffman product preferentially. And one of the tactics that we have to do this is to use what's called a sterically hindered or a bulky base. For example, look at this table here. In the first entry, we're using a small base. And when I say small, it has a very small carbon chain. And the Zystev product is formed preferentially. Now, if I take that small base and make it bulky or sterically hindered, like I put a bunch of carbons on it, So we call that a bulky base or sterically hindered base. Notice now how the Hoffman product predominates. It like the product distribution basically flips. And if we use a really, really, really bulky base, then we almost get that exclusively, get the Hoffman product exclusively. So using sterically hindered bases favor the Hoffman product. Now let's kind of take a look at why. So I'll use the same substrate here. And again, I'll draw my two hydrogens. And I'm kind of going to exaggerate this, but I do it to emphasize a point. Here is our big, bulky base. Now, which hydrogen, again, I'll label these the same way, beta 1, beta 2, which hydrogen do you think that base would have an easier time getting to, given the fact now that it's bulky, it's sterically hindered? It doesn't want to go after this hydrogen in the middle as much because it's more in the middle where there's a bunch of other stuff to deal with sterics. It's a lot easier to get to something on the outside to do an E2 elimination. So that is why um, bulky bases will preferentially form the Hoffman product. Now, there are a series of bulky bases that I want you to know. Um, so bulky bases to know. One of the most common ones is known as tert butoxide or T-butoxide. Very commonly, you'll see it with the counter ion. You'll see it as like TBUOK. Like TBUO is tert butoxide. And potassium is a very common counter ion to it. Another one is diisopropylamine. It's got a couple of very bulky isopropyl groups on it. And then a third one to know is triethylamine. So I would just memorize those names and structures. All right, let's do a little bit of practice here. So what we're going to do is predict the E2 products for the reactions we're going to draw. And I want you to do both major and minor. Okay, so the first thing, we're going to assume this is E2. But if we kind of take a look here, we have the methoxide ion. That's an O methyl group. So CH3O minus. Very small base, and it's also very strong. Right? But again, let's assume this is going to undergo an E2 reaction. So the first thing that you will want to do is identify your potential beta hydrogens. So I have one here. I'm going to draw in. And I have one here that I'll draw in. And that's the exact same as this one on that side, on the other side. So these two are the same. It won't matter if I pull one or the other off. So let's draw the E2 elimination of both of them separately. So let's say I pull off the one on the top corner here. Oops, we'll have the Cl. We'll form a double bond there. So that's pulling this one off. Now what if I pull the other one off here? I would get this double bond. Now, since this base is small, it's not bulky, it's not sterically hindered, we want the preferential product, the major product is going to be the Zystev product, the more stable alkene. And that's this one. Now it might form a little bit of the less stable product. We don't know how much, and I don't expect you to know percentages. I just want you to be able to recognize that one will be major and know which one's the major, and one will be minor. And again, know which one's the minor product. All right, let's contrast that with this one. I'm going to use the same exact substrate. But now that I look at the base, this is one of those big, bulky, strong bases I want you to memorize. Tert butoxide is a bulky base. Now, let's draw all the possibilities again. So again, those are two possible products. We're going to have the exact same products, but the difference is now that we're using a bulky base, the major product is the Hoffman product, and the minor product is the Zystev product because a bulky base was used. Now let's look at another reaction. All right, so again, let's assume we're going to do an E2 elimination here. What I want you to do is kind of quickly just pause the video and identify where your alpha hydrogens, or I'm sorry, beta hydrogens are at. So if this is the carbon with the leaving group, here's a beta hydrogen here. Here's one here. What about the other carbon on the other side? This one doesn't have any beta hydrogens, which is fine. We just won't focus on that one. So now let's draw the result of pulling off one or the other beta hydrogen. So if I pull off this one here first, I get this double bond. If I pull off the other one, I get that double bond. Now, how do I decide which one is the major or the minor? Well, I'm going to look at my base. Is the base big or small? So OMe, methoxide, should kind of already commit that to memory. That's a small, strong base. So this is going to form the Zystev product preferentially. And the Hoffman product will be the minor product. All right, let's look at one more. All right, so again, we're assuming E2 will be the mechanism here. And so we're going to identify all of our beta hydrogens. Well, we got one here. So this is the carbon with the leaving group. I go one carbon over, there's a beta hydrogen there. Do the same thing, there's a beta hydrogen there, and same thing there. Now, what do you notice about all three of those? All three sets of beta hydrogens are the same. Doesn't matter which one you pull off, you're going to get the same product each time. Doesn't matter what the base we're using is, because here in this particular example, we can only get one constitutional isomer. So which one do we pull off? Doesn't matter, pick one. Let's say I pick this one off here and I get that. That's the exact same product as this one, which is the same as that one. They're all the same product.